Hello everyone, I am Ramon Ramas, part of the academics committee, and I will be teaching about partial fraction decomposition under the FND math subject. So for the outline, first we would have an introduction on what partial fraction decomposition is. Then we will tackle cases and examples, particularly case 1, distinct linear factors, case 2, repeated linear factors, case 3, irreducible quadratic factors, and case 4, repeated irreducible quadratic factors. Then, we'll have a summary of the steps on how to do partial fraction decomposition. So first, what is partial fraction decomposition? Partial fraction decomposition is the method used to decompose a given rational expression into simpler fractions. Let's say we have a fraction whose numerator is x to the 15th power while our denominator is x to the 20th power. If we would integrate or even derive this fraction, it would take a long time. So using partial fraction decomposition, we could cut down the huge fraction into smaller parts or simpler fractions so that it is easy to use in our problem solving. So let's tackle on our first case. Case 1. Distinct linear factors. Distinct linear factors. If the factored form contains a distinct linear factor, ax plus b, then the partial fraction decomposition will contain a term of the form a divided by ax plus b. So this case says that for each linear factor that you have ax plus b, that will know how many terms of the form a divided by ax plus b of the simpler fractions you will have. If you're wondering how this works, let me show you an example. An example would be 6x minus 9 divided by x squared minus 2 minus 8. So we could see that the numerator is x raised to the first power, while the denominator is x raised to the second power. So we could simplify 6x minus 9 divided by x squared minus 2 minus 8 by factoring the denominator first. So 6x minus 9 divided by x squared minus 2 minus 8 is also equal to 6x minus 9 divided by the quantity of x minus 4 times x plus 2. How did we get these values? We just took out the factors of x squared minus 2 minus 8. So now that we have our factored denominator, we could see that there are two distinct linear factors, 1 and 2. So for each linear factor we have, we'll make the form a divided by ax plus b happen. So 6x minus 9 divided by the quantity of x minus 4 times x plus 2 would be equal to a divided by x minus 4 plus b divided by x plus 2. So since we have two linear factors, we would have two simpler fractions. We could also multiply the whole value by its least common denominator. The least common denominator would be x minus 4 times x plus 2. Why is that? Since we took the simpler fractions from the original denominator, which is 6x minus 9 divided by x minus 4 times x plus 2, we could say that its denominator is already the lowest common denominator. So after multiplying, we would have an equation of 6x minus 9 is equal to the quantity of a times x plus 2 plus the quantity of b times x minus 4. We could further simplify by multiplying a to x plus 2 and b to x minus 4. So the equation would be 6x minus 9 is equal to ax plus 2a plus bx minus 4b. So the next step in this would be making a system of equations, since we would want to equate all of the variables with that are x to each other. And we also want to equate all of the variables without an x to each other. So first, we would use system of equations. Also, for all the variables of x, we'll get their coefficient. So in the left side, we only have 6x. Its coefficient is 6. And on the right side, it would be ax and bx. So 6 is equal to a plus b. Next, all of the coefficients without a variable on the left side is negative 9. And it's equal to 2a and negative 4b. So negative 9 is equal to 2a minus 4b. The next step is trying to cancel out one letter to obtain the value of the other letter. So in this example, we could multiply the first equation by 4 so that we could get the equation 24 is equal to 4b plus 4a. So we could see that 4b and negative 4b of the second equation, if added together, becomes 0. So if we add the values of the two equations, we would have 15 is equal to 6a. So we're close to getting our value for a. So if we divide both sides by 6, we would get 15 over 6, or if we simplify it further, 5 over 2. So 5 over 2 is the value of our letter A. So for our value of letter B, we'll just plug in our value of letter A to one of the equations to get the value of letter B. So after we do that, the value of our letter B would be 7 over 2. The next step, which some people might forget, is to plug in our values for A and B into the original form of the simpler fractions, which is this one. So if we plug it in, our final answer would be the simple fractions of 6x minus 9 divided by x squared minus 2 minus 8 is 5 divided by 2 times the quantity of x minus 4 plus 7 divided by 2 times the quantity of x plus 2. So that is how you get the distinct linear factors case. So for the next case, we would have repeated linear factors. Repeated linear factors. If the factored form contains a distinct linear factor ax plus b raised to n, then the partial fraction decomposition will contain a term of the form a divided by ax plus b plus b divided by ax plus b squared, and so on and so forth until we reach the ax plus b raised to n. So for example, if our n were 3, we would only have until c raised to ax plus b raised to 3. And for 4, it will be until d divided by ax plus b raised to 4, and so on and so forth. So the number of repeated linear factors will depend on the exponent of the linear factor. So for an example, 5x minus 7 divided by x squared minus 8 plus 16. So if you want to simplify the denominator, you'd get its factors, and its factors is x minus 4 squared. Since we have 2x minus 4, we could just combine it to become x minus 4 squared, which is this. And using what we learned a while ago, the form would be 5x minus 7 divided by x minus 4 squared is equal to a divided by x minus 4 plus b divided by the quantity of x minus 4 squared. So with that, it's similar to case 1 where the numerators are just single letters. We can then multiply both sides by the LCD, which we talked about is the factors of the original equation. It's x minus 4 squared. After multiplying, we would have the equation 5x minus 7 is equal to the quantity of a times x minus 4 plus b. We could further simplify by multiplying a times x minus 4. Our equation would be 5x minus 7 is equal to ax minus 4a plus b. Here, we can use system of equations since we want to equate the x's and the non-x's. So for the x's, we have the coefficient of 5 on the left side, and on the right side, it only has the coefficient of a. So the first equation is 5 is equal to a. For the coefficients, it will become negative 7 is equal to negative 4a plus b. So in our first case, we wanted to remove one of the letters in order to get the value of the other letter. But if you could see here in the first equation, the value of a is already given, which is equal to 5. So we could just plug in 5 here. It becomes negative 7 is equal to negative 4 times 5, which is negative 20, plus b. We then add 20 to both sides to move the negative 20. And then the answer would be b is equal to 13. So our final answer is we plug in the values of a, which is 5, and b, which is 13, and we get final answer of 5 divided by x minus 4 plus 13 divided by x minus 4 squared. So in my opinion, repeated linear factors are easier than linear factors. So for our next case, case 3, irreducible quadratic factors. So what are irreducible quadratic factors? If the factored form contains an irreducible quadratic factor ax squared plus bx plus c, then the partial fraction decomposition will contain a term of the form ax plus b divided by the quantity of ax squared plus bx plus c. So, if the quadratic factor ax squared plus bx plus c cannot be reduced to, an example, another linear factor, we would have to use the ax squared plus bx plus c in the denominator, but its numerator, instead of being just a, will now be ax plus b. So for example, x squared plus 5x plus 4 divided by the quantity of x squared plus 2 times the quantity of x minus 1. So at first glance, we would think that the numerator and denominator's powers are equal. But if you would multiply x squared plus 2 times x minus 1, you would see that the highest power in the denominator is actually 3. So this is for partial fraction decomposition. So x squared plus 2 doesn't have any linear factors out of it. So we will have to use the quadratic factor as itself. So this is a combination now of case 1, which is linear factors, and case 3, which is irreducible quadratic factors. Do note that in most problems, you wouldn't be only just be using one case. We could be using multiple or even all the cases at the same time to decompose a fraction. So quantity of x squared plus 5x plus 4 is divided by x squared plus 2 times x minus 1 is still the same. Next, we'll now use the cases that we know already. So x squared plus 5x plus 4 divided by the quantity of x squared plus 2 times x minus 1 is equal to ax plus b divided by x squared plus 2 plus c divided by x minus 1. So we need to be careful on where do we put our ax plus b and c. Some students might put ax plus b under x minus 1, which would result in them getting the wrong answer. So always remember that ax plus b has the denominator of an x raised to the second power, which is this. So now we could multiply both sides by its lowest common denominator, which is x squared plus 2 times x minus 1. So the answer for that would be x squared plus 5x plus 4 is equal to ax plus b times x minus 1 plus c times x squared plus 2. Now we would be multiplying the quantity of ax plus b to x minus 1 and the quantity of c times x squared plus 2. After multiplying, we would have the answer of x squared plus 5x plus 4 is equal to ax squared minus ax plus bx minus b plus cx squared plus 2c. So now we have three different kinds of powers of x. We have x to the 0th power, x to the first power, and x to the second power. So using system of equations, we could equate all of the x's to the 0th power to each other, the x's to the first power of each other, and x to the second power to each other. So for x to the second power, we would have 1 is equal to a plus c. For x to the first power, we would have 5 is equal to negative a plus b. And for x to the 0th power, or the coefficients without any x's, 4 is equal to negative b plus 2c. So using system of equations, we try to get an equation that has only a single letter. So for example, the first and second equation have a and negative a. So we could add these together to get a removed from the equation. So it becomes 6 is equal to b plus c. So, and now we have 6 is equal to b plus c, and 4 is equal to negative b plus 2c. We could add those together to remove b, since we have b and negative b. And then if we add these together, we would have 10 is equal to 3c. If you divide both sides by 3, you would have a value of c is equal to 10 divided by 3. Our next step would be inputting our c into an equation to get the other letter. So for example, we could input 10 divided by 3 of c to the equation of x squared, so that we could get 1 is equal to a plus 10 over 3. After we do that, the answer would become a is equal to negative 7 over 3, and we will repeat the process for letter b, which we would get b is equal to 8 divided by 3. And now, don't forget to input a, b, and c to the partial fractions, so that our final answer would be negative 7x plus 8 divided by 3 times the quantity of x squared plus 2 plus 10 divided by 3 times the quantity of x minus 1. If you want to check if your answer is correct, just try adding your partial fractions and see if you get the given fraction from a while ago. So if you add these two, you're going to get x squared plus 5x plus 4 divided by x squared plus 2 times x minus 1. And now, for the last case, we have repeated irreducible quadratic factors. If the factored form contains a repeated irreducible quadratic factor, ax squared plus bx plus c to the power of n, then the partial fraction decomposition will contain a term of the form ax plus b divided by ax squared plus bx plus c plus cx plus d divided by the quantity of ax squared plus bx plus c squared, so on and so forth, until yx plus z divided by ax squared plus bx plus c raised to n. So it is similar to case 2 where instead of repeated linear factors, we have repeated irreducible quadratic factors. So the number of quadratic factors we would have repeated is based on the power of n. So for an example of this, we have example x cubed plus 3x squared plus 2x plus 1 divided by quantity of x squared plus 2 squared. So at first glance, you would look at the numerator having a higher power than the denominator because x cubed is greater than x squared. But if we would expand the quantity of x squared plus 2, it will become x fourth, which is higher than x cubed. So since it is already a repeated irreducible quadratic factor, it would stay the same here. And now we would use the knowledge we know from case 4 to implement its partial fractions. So x cubed plus 3x squared plus 2x plus 1 all divided by x squared plus 2 squared is equal to ax plus b divided by x squared plus 2 plus cx plus d divided by x squared plus 2 squared. So we could get the least common denominator, which you all know is the original denominator, which is x squared plus 2 squared. Sorry for my handwriting. After multiplying it, we would have x cubed plus 3x squared plus 2x plus 1 is equal to ax plus b times x squared plus 2 plus cx plus d. You could simplify it further by multiplying ax plus b times x squared plus 2. Our simplified version of the equation would be x cubed plus 3x squared plus 2x plus 1 is equal to ax cubed plus 2ax plus bx squared plus 2b plus cx plus d. So, using system of equations, you would actually have 4 equations since we have x to the 0th power or the coefficients without an x to the 1st power, x to the 2nd power, and x to the 3rd power. So after equating each of their coefficients, we would have the 4 equations, which are 1 is equal to a, 3 is equal to b, 2 is equal to 2a plus c, and 1 is equal to 2b plus d. As you can see, in our first 2 equations, it just gives the value of the a and b. So a is equal to 1 and b is equal to 3 based on the system of equations. We then could input a and b to each equation to get the value of c and d. So for the third equation, it could be 2 is equal to 2 times 1, which is 2 plus c, and minus 2 from both sides, and you get c is equal to 0. And input b in the fourth equation so that we have 1 is equal to 2 times 3, which is 6, plus d. And then get the difference of 6. And then we have d is equal to negative 5. Again, don't forget to input the values of a, b, c, and d to your partial fractions to get the final answer. So the final answer would be x plus 3 divided by x squared plus 2 plus negative 5 divided by x squared plus 2 squared. Cx is gone because c is equal to 0 and 0 times x is equal to 0. For a summary of what we have just learned, partial fraction decomposition is the process of decomposing a rational expression to smaller fractions. Our steps would be simplify the rational expression to its factors, determine the cases needed to be used in its decomposition. So multiple cases can be used in one expression. So case 1, case 2, case 3, and case 4 can all be used together. Simplify the equation by multiplying by its lowest common denominator, which is the denominator of the original fraction, and make equations based on the coefficients of the same variables, which basically means get the equations based on the power of the x it has. And then use system of equations to obtain the numerators of the smaller fractions, which are a, b, c, d, and so on and so forth. And once you have those values, plug in the obtained values into your final answer. So this is how you get partial fraction decomposition. If you have any questions, you can contact us at chen.acads@gmail.com or message us at facebook.com/chen.acads. Once again, I am Ramon Ramas, and thank you for listening to our CHE 101 tutorial video. I hope that we could see you watch more videos in the future. Thank you.